Assalamualaikum warahmatullahi wabarakatuh. My name is Muhamad Arif, Danial bin Zazuli, and I'm a student under the supervision of Dr. Muhammad Azizi bin Nawawi. In this video, I will be presenting my final year project titled Fluorescent Behavior of 9-Dicyannovinyl Julolidine in Solvents of Different Viscosities and Polarities. There are 5 main parts I would like to discuss in this video: introduction, literature review, research methodology, results and discussion, followed by conclusion and recommendation. At the end of my presentation, I will show all the references I have cited for my project. I will first elaborate on the definition of solvents and their types. Solvents play a crucial role in many chemical processes and everyday application, and they exist in various states including liquid, solid, gases, and supercritical fluids. Water, being one of the most commonly known solvent, is often referred to as the universal solvent due to its remarkable ability to dissolve a wide range of substances. This unique property makes water indispensable in numerous biological, chemical, and industrial processes. As for the type of solvent, they can be broadly categorized into 2 types, which are polar solvent that can dissolve in polar substances and non-polar solvent that dissolve in non-polar substances. Many commonly used solvents, however, pose significant health and environmental risks. Common hazardous solvents include dichloromethane, toluene, xylene, white spirit, acetone, and ethyl acetate. Exposure to high concentration of this solvent can lead to severe health consequences such as unconsciousness or even death. Even at low levels, these substances can cause immediate health issues including dizziness, headaches, and respiratory problems. In response to the demand for safer and more eco-friendly options, green solvents have been developed. The sustainable alternatives are designed to minimize health and environmental impacts characterized by their ecological, biodegradable, and sustainable properties. Green solvents aim to reduce the use of hazardous solvents, offering benefits such as increased reaction rate, lower operating temperatures, improved selectivity, and non-volatility. Incorporating green solvent into industrial and laboratory practice promote more sustainable and safer chemical processes. Deuterated solvents are a type of green solvent formed by mixing 2 or more components. These components create an eutectic mixture, resulting in a melting point significantly lower than that of the individual substances. DES offers several environmental benefits, making them a preferred choice in sustainable chemistry. They are biodegradable because they can break down naturally, reducing environmental impact. They are also sustainable as they are made from renewable resources, which can contribute to long-term environmental health. They also pose minimal health risks, making them safer for human use due to their low toxicity. Their non-flammable properties reduces risk of fire hazard, and lastly, their low risk of explosion enhances safety in handling and storage. However, one of the challenges with DES is their generally higher viscosity compared to traditional solvents. This characteristic can affect their handling and mixing efficiency, requiring careful consideration in their application. For our problem statement, green solvents such as deep eutectic solvent and ionic liquids exhibit elevated viscosity at room temperature. This high viscosity significantly limits their broad industrial utilization despite extensive research progress in developing eco-friendly solutions. Furthermore, there is a knowledge gap regarding the viscosity of green solvents. Specifically, there is a limited understanding of how their chemical properties and interaction with solutes affect their flow behavior. This lack of comprehensive knowledge hinders the effective application and optimization of green solvent in various industrial processes. There are several significant to this study. The first one is to gain an understanding of the factors that contribute to this high viscosity, including the unique chemical properties and interaction with solutes. Furthermore, this study will provide insight into the molecular interaction and structural dynamics within the green solvent. Last but not least, this study investigated the behavior of DCVJ as a fluorescent dye in green solvent with varying viscosity and polarities. Moving on to the objective of the project, the first and foremost is to synthesize a variety of molecular and deep eutectic solvent with different viscosity and polarities. Our second objective will be to analyze the chemical and physical properties of DES using tools like areometer, FTIR, MMR, UV visible, and fluorescent spectrometer. The third objective will be to explore the relationship between fluorescent signals, polarity, viscosity of deep eutectic solvent using the Foster-Hoffmann equation. For the first part of literature review, let's first dive into the rotational aspect of the DCVJ molecule, which are crucial for understanding its behavior in various environments. Here we see the chemical structure of DCVJ. This compound is characterized by its duolidine core, which is a fused ring system, and the dicyanovinyl group attached to it. The nitrogen atom is part of the duolidine core, and the two cyanide groups are attached to the vinyl group. In the second diagram, we observe the rotational axis within the DCVJ molecule. The rotation primarily occurs around the single bond that connects the duolidine moiety to the dicyanovinyl group. This single bond allows for the rotation of the dicyanovinyl group relative to the duolidine core. As for the utilities of DCVJ, it can be effectively used to monitor the pH of solution. Furthermore, DCVJ is highly effective in detecting alteration in its viscosity and polarity within the microenvironment, as the fluorescent and rotational behavior of DCVJ are sensitive to the surrounding viscosity and polarity. DCVJ also serves as an excellent fluorescent probe for studying molecular interaction. With its fluorescent properties, DCVJ can visualize and analyze interaction between molecules. DCVJ is a versatile compound with wide-ranging application in biochemistry, biophysics, and molecular biology. Its unique properties make it an invaluable tool for scientific research and industrial application, contributing significantly to our understanding of biological systems. While DCVJ has several valuable utilities, it also has some significant limitations that needs to be considered. Photobleaching is a major limitation of DCVJ. Photobleaching refers to the irreversible loss of fluorescence when the molecule is exposed to light for an extended period. This phenomenon can significantly impact the accuracy and reliability of fluorescent measurements, especially in long-term experiments. Another limitation of DCVJ is self-quenching. Self-quenching occurs when the concentration of the fluorescent molecule is too high, leading to the interaction between them that result in a decrease in fluorescent intensity. DCVJ is also vulnerable to interference from other substances in the environment. Various factors such as pH, ionic strength, and the presence of other fluorescent molecules can interfere with the fluorescence of DCVJ, leading to unreliable results. Now let's move on to the research methodology. The study started off with synthesizing the deep eutectic solvents and then proceeded to determine the physical and chemical properties of the solvent with three instruments: Fourier transform infrared spectrometer, nuclear magnetic resonance spectrometer, and areometer. The next step involved preparing the fluorescent dye stock solution to measure the lambda of mass absorption with ultraviolet visible spectroscopy, and then the lambda mass of emission with fluorescence spectroscopy. Finally, we correlated the fluorescent signal to the viscosity of DES with Foster-Hofmann equation. Starting with the first objective, which is the synthesis of DES, this method utilizes 5 different hydrogen bond donors in varying ratios with the same hydrogen bond acceptor, as shown in the table. The DES were prepared using the direct mixing method. Firstly, the HBA and HBD were weighted according to their respective ratios. After grinding the mixture together, it will then be heated and stirred at 40 degrees Celsius until a colorless liquid is formed. The mixture was then dried at 50 degrees Celsius for 8 hours in a vacuum oven. After taking it out, the solution will then be stored and cooled in a desiccator. Several analytical steps were used for the physical and chemical characterization of the DES in the study. FTIR spectroscopy was conducted by using the infrared 35 Perkin element spectrophotometer model, scanning wavelength for 400 to 600 nanometer with a resolution value of H. Each spectrum was averaged over 4 scans. As for MMR, the model that was used was the Bruker Advanced 400 spectrometer. The DES sample were dissolved in deuterium oxide and then subjected to 500 scans for the 1H analysis. The areometer model that we used to measure viscosity was MCR300 Physica, applying shear rates from 1 to 50 per second across 20 points. 10 ml of each sample was injected into the cylinder, and the value of viscosity was determined by dividing the shear rate by the shear stress ratio. This method facilitated a thorough characterization of the DES, yielding detailed insight into their structural and rheological properties, thereby addressing the second objective of the project comprehensively. Next, UVB scanning was conducted by using lambda 35 Perkin element instrument to determine the lambda mass absorption of the solvent. Each sample containing 4.88 micromolar of the DCVJ stock solution was scanned from 200 to 800 nanometer with a speed of 480 nanometer per minute. The absorption spectra was recorded to determine the lambda mass of absorption. As for the fluorescent spectroscopy, LSS Perkin element model was used to determine the fluorescent intensity and the lambda mass emission for each sample. The scan was done within the range of 200 to 800 nanometer. The excitation and emission were done at 440 and 550 nanometer respectively. The slit width for both in and out was set to 15. The resulting spectra yielded data on the maximum emission wavelength and fluorescent intensity, which are critical for evaluating the fluorescent property of the CBJ as a fluorescent dye in various solvent environments. These measurements were essential for assessing how different solvents influence the fluorescent behavior of the compounds, thereby contributing to the second objective of the project. For the third objective, the Foster-Hoffmann equation was used to correlate the fluorescent signal to viscosity. In the result and discussion section, the FTIR analysis of choline chloride urea reveals significant shift in key functional group compared to the starting materials. The CH stretching, OH bending and OH stretching vibration all shift to lower wave numbers, indicating changes in the electronic interaction within the molecule. The shift of the CH stretching frequency to a lower wave number suggests altered electron density around the CH bonds. The OH bending and stretching vibration indicate stronger hydrogen bonds, as the energy required to stretch or bend this bond decreases when involved in more robust interactions. Complementing the FTIR spectra, the NMR findings offer detailed insight into the molecular structure of the choline chloride urea sample. The spectrum shows 4 distinct peaks, each corresponding to different hydrogen environments within the compound. Peak A at 4.7 ppm and identified as a singlet represent the CH2 group from choline chloride, indicating non-neighboring hydrogens. Peak B at 3.99 ppm appears as a doublet at doublets and is assigned to the OH group from choline chloride, influenced by adjacent hydrogens. PC at 3.5 ppm is a multiplet representing another CH2 group from choline chloride interacting with multiple neighboring hydrogens. Finally, Peak D at 3.14 ppm is a singlet corresponding to the CH3 group from choline chloride, suggesting non-neighboring hydrogen influences. This MLR result confirm the presence and structural composition of the components, providing crucial insight into their purity and potential chemical behavior. In the FTIR analysis of choline chloride malonic acid, significant shifts are observed in the C double bond O stretching and OH stretching vibration compared to the initial materials. The C double bond O stretching vibration shifts to a lower wave number, reflecting changes in the electron distribution around the bond. Similarly, the OH bond stretching vibration also shifts to a lower wave number, indicating alteration in electronic interaction within the molecule. Additionally, a new peak corresponding to CN stretching vibration suggests the formation of interaction between the components. Applying the same methodological approach, the NMR result yield critical insight into the structural composition and purity of the component within the mixture. These findings are essential for understanding the chemical behavior and potential application of the synthesized compounds. In the case of choline chloride glycerol mixture, a shift was observed in the CO stretching and the OH stretching vibration. Specifically, the OH stretching vibration shifted to a lower wave number, similar to the CO stretching observed in pure choline chloride. Conversely, in the starting material glycerol, both the CO and OH stretching vibration shifted to a higher wave number. The subsequent sample is choline chloride 1,4-butanediol. Shifts were observed in the CH bending and OH stretching vibration. For the pure choline chloride, the OH stretching vibration shifted to a lower wave number. In contrast, for the 1,4-butanediol starting material, shifts to higher wave numbers were observed for both the OH and CH functional groups. For the FTIR analysis of the last sample, which is choline chloride ethylene glycol, noticeable shifts were observed in the CO stretching vibration of ethylene glycol and choline chloride starting material, both shifting to a higher wave number. Conversely, the OH stretching vibration in both starting material shifted to a lower wave number. These FTIR findings highlight significant changes in electron distribution and molecular interaction following the formation of choline chloride ethylene glycol complex. The NMR spectra presented along with them primarily serve for determining the chemical structure of the samples. Proceeding to the viscosity measurement section, the rheometer result indicated Newtonian behavior, signifying that the viscosity of the sample remained constant across varying shear rates. For the UV-Vis, the lambda mass absorption of DCVJ in each molecular solvent were acquired. The lambda mass is categorized into viscosity and polarity. The polarity index, represented by the dielectric constant, is utilized to determine the polarity of the solvents. The graphical representation reveals there is no consistent trend observed for either polarity or viscosity, indicating that DCVJ is sensitive to both factors. This finding underscores a complex relationship between solvent properties and the absorption characteristic of DCVJ. Similarly, for DES, there is no consistent trend for either polarity or viscosity, which suggests that DCVJ exhibits sensitivity to both factors. For fluorescence spectroscopy, the acquired fluorescence spectrum analysis of molecular solvent identified the maximum intensity for each solvent. The spectrum analysis revealed no consistent trend concerning both polarity and viscosity, highlighting DCVJ sensitivity to these factors. This stands in stark contrast to the fluorescence finding for DES, where a clear correlation with viscosity is observed. As the viscosity of the DES sample increases, the maximum emission wavelength, lambda mass, also increases, indicating that DCVJ exhibits sensitivity to viscosity, particularly within the DES environment. The correlation between fluorescence signal and viscosity, as described by Foster-Hoffmann equation, varies significantly across different solvent types, reflecting their distinct behavior in terms of fluorescence intensity. For both polar and non-polar molecular solvent, there is a clear trend where increasing viscosity corresponds to an increase in fluorescence intensity. This positive correlation indicates that as the viscosity of the solvent rises, so does the fluorescence intensity. Similarly, the DES sample also demonstrates a positive correlation between viscosity and fluorescence intensity, suggesting that DES and molecular solvent are equally effective in application, requiring high fluorescence intensity with increased viscosity. In summary, the Foster-Hoffmann equation reveals a strong positive correlation between viscosity and fluorescence intensity for both molecular solvent and DES. In conclusion, 5 distinct DES with varying viscosity and polarity were synthesized and characterized using FTIR, 1H MMR, and rheometer techniques to confirm their chemical and physical properties. The spectral data reveal shift in functional group, confirming intermolecular interaction between hydrogen bond acceptor and donor. The synthesized DES exhibited properties characteristic of non-polar solvent with a notable increase in fluorescence intensity, positively correlating with increased viscosity. For molecular solvent, the fluorescent emission of the DCVJ dye is displayed a consistent trend with viscosity across both polar and non-polar environments, underscoring the dye sensitivity to changes in polarity. Overall, a linear correlation between viscosity and fluorescent intensity was observed, indicating that an increase in viscosity results in a corresponding increase in the fluorescence signal. Recommendations for future work include exploring alternative dye to demonstrate variation in fluorescent behavior and developing different types of iterative solvents to enhance fluorescent performance. Additionally, investigating further fluorescent parameters such as fluorescent quantum yield and lifetime will provide a more comprehensive analysis. It is also advisable to examine other categories of green solvent, including ionic liquids and supercritical fluids, for potential application and comparative studies. These are all the references I have used for my project, and that will be all of my final year project. Thank you.